a concrete example to explain chi-square goodness of fit test. In the USA, Federal Bureau of Investigation collects data on crimes. A violent crime is classified into murder, rape, robbery, and assault. Murder, rape, robbery, and assault. Now, table give us relative frequency distribution of these crimes in the year 2000. Murder, rape, robbery, assault. 0.011, 0.063, 0.286, 0.64, total 1. Now, a random sample of 500 violent crimes were taken in the year, say, 2020. A random sample of 500 violent crimes reported in 2020, and the frequencies, the year is 2020, murder, rape, robbery, assault. Murder 3, 37, 154, 306, a total of 500. As you can see, this is a multinomial data because it has 4 categories. Multinomial, 4 categories. This is the relative frequency in 2000. This is the actual observations in 2020. Now suppose that we want to test whether the distribution of violent crimes in 2020 has changed compared to the violent crimes in 2000. We want to test whether the distribution of violent crimes is different from the distribution of violent crimes in the year 2000. So it is a test of goodness of it. How fit is the observed data to an assumed distribution? The assumed distribution is the distribution in the year 2000. Whether our observed data fits to the assumed distribution, that is one point. The second point is it is a multinomial population. Now what is the population? The population is violent crimes in the year 2020. Violent crimes in the year 2000, the entire population, not 500. Variable is type of violent crimes. Population is last year's violent crimes. Variable is types of violent crimes. Categories are murder, rape, robbery, and assault. And we want to perform the hypothesis test. The hypothesis test we want to perform is last year's violent crime, the violent crime of 2020, the violent crime of 2020, or the distribution of the violent crime of 2020 is same as 2000. and H1, the distribution of violent crime of 2020 is different from 2000. Null hypothesis, the distribution in the year 2020 is same as 2000. H1, the distribution is different. Now, the basic idea behind the chi-square goodness of fit test is to compare. The basic idea is to compare what is known as observed frequency. The observed frequency. This is the observed frequency 337, 154, 306 with the frequencies expected or expected frequencies. If the distribution of violent crime in the year 2020 is same as the distribution in 2000. That is, observed frequencies is compared to expected frequencies if the distribution of violent crime in the year 2020 is same as 2000. Now, as an example, in the year 2000, robbery was 28.6%. If the distribution is same in the year 2020 also, then the relative frequency of robbery, that is relative frequency must be 28.6%. Then only the distribution of violent crime in the year 2020 will be same as 2000. Now, in general, we compute each expected frequency denoted by E using the equation n into P. We count the expected frequency in each cell using the formula E is equal to NP. N is the sample size and P is the appropriate relative frequency. Now, the relative frequencies are given here. Now, in order to see the relative frequencies for the year 2020, relative frequencies are 0.01, 0.063, 0.286 and 0.64. Now, what we do is 500 is multiplied by 0.01, 3.5. 500 is multiplied by 0.063, 31.5. 500 is multiplied by 0.286, it is equal to 143. Then 500 is multiplied into 0.64 is equal to 320. These are the expected frequencies: 3.5, 31.5, 143, 320, and these are the actual frequencies. These are the observed frequencies. These are the expected frequencies. Now, the question is whether observed frequencies match reasonably well with the expected frequencies. If observed frequencies are more or less similar to expected frequencies, then the distribution of crimes in 2020 is similar to that of 2000. To answer this question, we need to estimate a number that measures how good the fit is. That number is the chi-square statistics. Let us see how with a simple example. Now, murder, rape, robbery, assault, observed frequency 3, 37, 154, 306, 500. Expected frequency 5.5, 31.5, 143, 320, 500. O minus E square 6.25, 30.25, 121, 196. Then O minus E square by E is equal to 1.136, 0.96, 0.846, 0.613, that is 3.555. As we have stated earlier, this quantity has chi-square distribution. So in order to see whether expected frequencies match reasonably well to the observed frequencies, we require a number. This number is obtained by this calculation. O minus E is not taken because if you take O minus E, it will be 0. O minus E is equal to 0. So, if you take O minus E here, the sum will be 0. So, we square the sum. Take O minus E square rather than O minus E. And divide the corresponding figure with E, the expected frequency. And doing this give us a statistics O minus E square by E, give us a statistics known as the chi-square statistics. And the sum of, so it will give us the chi-square subtotals, and the sum of chi-square subtotals, each one is a chi-square subtotal, and the sum of chi-square subtotals will give us the chi-square statistics. And the value in this case is equal to 3.555. And this statistics is used to test how well the observed frequencies fit to expected frequencies. And if H0 is true, observed and expected frequencies will be roughly equal. And it results in a small value for chi-square. But if observed and expected frequencies are very large, the chi-square will be very large. And in our case, the value of chi-square is 3.555, and the question is this due to sampling error, or is it large enough to suggest that H0 is false? Is this due to sampling error or large enough to suggest that H0 is false? To determine this, we use what is known as the chi-square goodness of it. This quantity is chi-square sigma O minus E square by E, as we have discussed in the previous class. So this quantity has chi-square distribution if H0 is true, and the degrees of freedom is 1 less than the number of variables, possible values of the variables. In this case, n is 4. So for this chi-square distribution has 4 minus 1, 3 degrees of freedom. Chi-square has degrees of freedom equal to 1 less than possible categories of the variable. Now, remember this, we reject H0 only when the value of chi-square is large. So chi-square goodness of fit is always right-tailed. Chi-square goodness of fit is always right-tailed because we reject H0 only when the chi-square value is large. Regarding the assumptions about the procedure, some authors suggest that all expected frequencies should be 5 or greater than 5. All expected frequencies be 5 or greater than 5. That is suggested by some authors, but not required always. Now let me conclude the steps. The steps are, we assume that all expected frequencies are 1 or greater. 1 or greater. All expected frequencies are 1 or greater. At most 20% of the frequencies are less than 5. Less than 5. At most 20% less than 5. At most, maximum. Then simple random sample. Then the steps are formulate H0 and H1. H0, all variables have specified distribution. Variable does not have the specified distribution. Then calculate the expected frequency for each possible value using the equation E is equal to NP. N sample size, P is the relative frequency. And see whether the expected frequencies satisfy assumption 1 and 2. That is very important, whether expected frequencies satisfy assumptions 1 and 2. And determine the level of significance, compute the value of chi-square and compare it with the critical values for what to say, k-1 degrees of freedom, and take a decision. In our example, it is 3.555. Degrees of freedom is 4 minus 1 is equal to 3, and critical chi-square is 7.815 for alpha is equal to 5% or P is equal to 0.10. So what we do is we accept H0. Chi-square critical is, remember this, chi-square critical is 7.815. The value we obtained is 3.555. So we accept H0. Accept H0 means the distribution of violent crimes in 2020 is similar to its distribution in 2000. So that is the conclusion. So the procedure is very simple. We have observed frequencies, we have expected frequencies. Take the difference, square it, divide each item with the expected frequency, sum it, we have the chi-square variable. Then for the degrees of freedom, number of categories minus 1, compute chi-square, compare it with the critical values, or you go to the p-value. And to take a decision about accept or reject H0. This is chi-square goodness of fit. For chi-square goodness of fit, we will have an assumed distribution. It may be normal, binomial, whatever it is. And we compare it with the, and what we do here is we want to find out whether the distribution that we have obtained is compatible with an assumed distribution.